Welcome to Relativity, Part 2. Last time we looked at the postulates and what happens to simultaneity, and we looked at some things about space-time. During this video series, you're going to look at time dilation. How does our motion in space affect our motion in time? And there's going to be some things you don't expect here. We're looking at chapter 40 in our book as a follow-up to this. And similar to last time, here are a lot of different short videos with some great insight.
Around 1900, all of physics, and particularly Einstein, was in trouble. They couldn't figure out how anything could move. Now, before you complain that I'm exaggerating, check out this cat. You can clearly see that the cat is moving away from Einstein at a constant velocity. But do a little sliding switcheroo, and suddenly it looks like Einstein's the one moving. This is the old-fashioned principle of relativity. But the point is that the switcheroo changes relative things, like position and velocity, and not absolute ones, like the separation of Einstein from his cat. Now for the problem. Before Einstein was even born, physicists showed that the speed of light was one of those absolute things which can't be changed by a switcheroo. So any switcheroo we do has to keep light moving at the same speed. But then it's obvious that we can't do our sliding switcheroo at all, which means we can't explain how anything other than light can move. Okay, I spoke too soon. There is one solution. Do you see it? We were assuming that our switcheroo had to keep every slice of time at the same, time. But there's no law of physics that says time is an absolute thing that can't be changed by switcheroos. So if we just rotate the slices of time while sliding them, then we can keep the speed of light the same and explain how things can move too. Of course, Einstein didn't figure out this special principle of relativity in 1905. It was already done by a guy named Lorentz 10 years earlier. But Lorentz just thought that this time rotation was a mathematical trick. And it took Einstein to step in and, you guessed it, propose that time rotation is real, that time really is relative, and that consequently, simultaneous events relative to one observer aren't simultaneous relative to another. Now that's a real switcheroo of perspective.
One major prediction of special relativity, confirmed by countless experiments, is time dilation. If you watch two identical clocks, one moving relative to you and one at rest relative to you, you'll observe the moving clock to tick more slowly. Really. Time dilation is nicely expressed in the twin paradox, where one twin stays at home and the other takes a high-speed rocket ride and returns years later. But their reunion is startling, for the stay-at-home twin is aged more than the traveling twin. True or just fiction? True indeed, as countless experiments have verified, with twin particles and twin clocks, not twin people. The explanation involves both twins not only being in different places in space, but experiencing different spans of time. Want to age slower than your kid sister? Then keep moving.
60-second adventures in astronomy. Number 10, special relativity. Does time fly when you're having fun? In 1905, Albert Einstein introduced the theory of special relativity, which said that if the speed of light is constant, then people must experience time differently. Which may sound impossible, but Richard Feynman later showed that you can prove it with just lights and mirrors. If you set up two mirrors, one of which had a flash bulb and a detector on it, you could build a clock which ticked every time the flash was reflected back to its original source. It would keep time perfectly, though it would make a slightly annoying alarm clock. But if you make this clock go past you very quickly, the light has further to travel, and since light always travels at the same speed, the moving clock runs slower than when it was at rest. So though time might not fly when you're having fun, a moving clock does tick more slowly than the observer's stationary clock. Which may have changed the way we see the universe, but doesn't always make for a good excuse.
Here are two starships, one at rest and the other in motion. When the moving ship passes the stationary ship, each fires its laser. Now, according to Einstein, the speed of the laser light doesn't depend on the motion of the ship. So we see both beams traveling side by side at the same speed. The crew of the ship at rest witness their laser beam traveling 12 light seconds in 12 seconds, and report that light travels at the speed of 1 light second per second. Correct. But what about the beam from the moving ship? Does it travel only 6 light seconds in 12 seconds? If so, the crew on board the moving vessel would report that light travels at only half speed? No, they wouldn't. But why not? According to Einstein, light always travels at 1 light second per second, regardless of the motion of the person who measures it. How do we fix our picture so that this is right? Part of the answer lies in the fact that the clocks on the moving ship slow down. As we stated earlier, if we must agree on the speed of light, we may have to disagree on the measure of time. If the clocks on board the moving vessel ran only half as fast as the ones at rest, our problem would be completely solved. The light beam from the moving ship would still travel 6 light seconds, and with the slow clocks, it would take only 6 seconds for this to happen. And the crew would report that light travels at precisely 1 light second per second. But it turns out the clocks don't slow down enough to be the whole answer. So in a minute, we'll look at the second part of the answer.
And of course, this isn't a statement about clocks. It is time itself that slows down. Right? Over the last 100 years, countless experiments have shown without a doubt that it is time itself that slows down. But why does it occur?
A clock is any device that counts events that occur at regular intervals. The event that drives a clock can be just about anything. The swing of a pendulum, the bounce of a ball, the unwinding of a spring, or the changing current in an electric circuit. Any regular event will do. Let's imagine constructing a clock in which a beam of light bounces between 2 mirrors. Whenever the light strikes the bottom plate, the clock advances. If 2 such clocks are stationary, then we would expect the time indicated on each clock to be precisely the same. But what happens when one clock is in motion? Notice although both clocks are identical, the moving clock ticks slower than the one at rest. In order to understand why, notice the paths of the light beams. The light in the stationary clock travels up and down vertically, but the light beam in the moving clock must travel a longer diagonal path. Since both beams travel at the same speed, and the upper beam travels a longer distance, the stationary observer sees the moving clock run slower than his own. This slowing down of clocks in motion is known as time dilation. It should be stressed that a person moving along with the moving clock would notice nothing unusual at all. The clock and the flow of time would seem to progress normally. According to this observer, he is at rest and the other observer is moving past him. According to him, it is the other clock that is running slowly. The flow of time in Einstein's universe is entirely relative.
I hope you enjoyed all of that. I'll see you in class.